Hello everyone, this is Vani from R.M.K College of Engineering and Technology. In this video, we are going to discuss about channel models. So, the main objectives are to understand the significance of channel and types of channel. We are going to analyze a special channel called as binary symmetric channel, and also we are going to calculate the channel capacity of binary symmetric channel. So, what is meant by channel? So, channel is the communication medium between the transmitter and receiver. If we see here, this section is transmitter and this section is receiver. So, in between the sender and receiver, channel plays an important role of communication where it carries the information in terms of bits and transmits through the receiver. So, it is very important that the channel is noise free so that whatever information is transmitted is reaching to the destination with minimum probability of error. So we are going to define what is discrete memoryless channel. Let us understand the physical meaning of discrete memoryless channel. Actually, it is a statistical model with an input X and output Y. That is a noisy version of X. That is when we are sending the information through the channel is adding some noise. In the channel, some noise is getting added. So Y is nothing but the noisy version of input X. Both X and Y are random variables and we call it as discrete channel. The meaning is that when both the alphabets X and Y have finite sizes, that's why it is called as discrete. The meaning of memoryless is when the current output symbol depends only on the current input symbol and it is not depending on any previous or future symbol. Then it is called as memoryless. So whatever I told, let us represent in terms of matrix representation. So if we take here the alphabet X and the symbols generated are from X0 to X1 and so on, right? So that is input X. This is the channel, right, where our noise is getting added and Y is nothing but noisy version of X with symbols Y0, Y1 and so on. So the input X with sample value X, this is a transition probability and this is output Y with sample value Y. So it is a simplified graphical representation of the channel. Now, the channel matrix can be represented in terms of stochastic process where row represents fixed channel input and each column represents fixed channel output, right? So row represent input, channel input, column represent channel output. So what is the interpretation out of this equation? If we are given with input prior probabilities, probability of xj, and the stochastic matrix is given, that is the matrix of transition probability, which is probability of yk by xj is also given, then we may calculate the probability of the various output symbol, which is probability of yk, right? So that's why this is called as channel model, where we are able to calculate the output probability based on channel transition matrix and input. So let us learn the various types of channel models available. One is lossless channel, which is a channel described by a matrix with only one non-zero element in each column, right? So only one non-zero element. If we see each column, only one non-zero element is available. So this channel can be represented as lossless channel, right? And the matrix representation and the alignment is given like this. If we see here, right, x1 to y1, it is 3 by 4, y2 it is 1 by 4, and x1 is not connected with y3, y4, y5. So we are stopping with y1, y2, right? The second row, if you take x2, it is connected with y3 with 1 by 3, y4 with 2 by 3. It is not connected with y1, y2 and y5. And the last case, if we consider x3, right? It is not connected with Y1, Y2, Y3, Y4. It is just connected with Wi-Fi, which is 1. Second type of channel is deterministic channel, a channel which is described by matrix with one non-zero element in each row is called a deterministic channel. If we see here, in each row, one non-zero element is there. So depending upon the requirements, these channels are used. The third category is noiseless channel. A channel is called as noiseless channel if it is both lossless and deterministic. So the channel matrix of the noiseless channel is given like this. Right? So it is a combination of lossless and deterministic. If we see here, each one is connected. X1 is connected with Y1, X2 is connected with Y2, and so on. So let us learn a special type of channel, which is binary symmetric channel. It is also a simple communication channel. The binary symmetric channel is of both importance. It has theoretical importance and practical importance. So it is a special case of discrete memoryless channel with the number of inputs j equal to 2 and number of outputs k equal to 2. The channel has two input symbol x0, x1 being binary. The possibilities are 0 and 1. And two output symbols y0 is equal to 0 and y1 is equal to 1. The channel is symmetric because the probability of receiving 1 if 0 is sent is same as the probability of receiving 0 if 1 is sent. That is error, right? 0 is sent and 1 is received, 1 is sent and 0 is received. The probability of error is same and it is represented by P. So this condition is called as probability of bit flipping. 1 transmitted, 0 received, 0 transmitted, 1 received. So it is called bit flipping. Now, if I represent the channel matrix, it is given by P is equal to 1 minus P, 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 1 minus P. What is the meaning of this? If I take the binary symmetric channel, 0 is transmitted and 0 is received at the output, right? 0 is transmitted but received as 1. So that probability of error I am representing as P. Sometimes we represent it as P with suffix E also. So if this is the probability of error, then the probability of correct reception is given by 1 minus P. The same applies here. We are transmitting 1. If we are receiving 1, it is a correct probability, which is 1 minus P. But if we are transmitting 1 and received as 0 at the output, then the probability of error is represented by P. Now our aim is to calculate the channel capacity of binary symmetric channel, which is very important breakthrough. At the same time, we need to understand what is the definition of channel capacity. So the channel capacity of discrete memoryless channel is defined as the maximum average mutual information in any single use of the channel, where the maximization is over all possible input probabilities. So mathematically, it is represented as channel capacity C is equal to maximum mutual information. I of x semicolon y is mutual information given with all the possible input probabilities, right? And the unit of this capacity is bits per use. Per use, how many bits are transmitted? So let us calculate the channel capacity of binary symmetric channel. So the same model I am assuming here, which we have taken earlier, the probability diagram of binary symmetric channel with the correct probability as 1 minus P and the probability of error as P. Now, as per the formula of channel capacity and the relationship between mutual information and entropy, I can calculate that C is equal to mutual information, probability of x0, probability of x1, I am assuming as 1 by 2. That is the probability of equal probability. Whether you're transmitting 0 or 1, the probability is equal, which is 1 by 2. And the probability of error, which is 1 is transmitted and 0 is received, or 0 is transmitted and 1 is received, is represented as P. The probability of correct transmission and reception, that is 0 is transmitted, 0 is received, 1 is transmitted, 1 is received, is represented as 1 minus P. Now, if I apply the formula and calculate the value, I know that the mutual information is given by the formula of probability of x0, y0, log 2 of probability of y0 by x0 by probability of y0. So here instead of P, I have taken PE to represent probability of error. Both are same. You can use either P or PE. So if I substitute all the values here, either it is PE by 2 or 1 minus PE by 2, if I substitute the values in this formula, I will get the formula as this, right? On expansion, if I expand and cancel the opposite terms, my equation becomes channel capacity C is equal to 1 minus P log 2P minus 1 minus P log 2 of 1 minus P, right? So this can be written as, we know that the formula for entropy is positive P log to 1 by P or negative P log to P. So I can represent this entire part as entropy. So this is the formula for channel capacity bits per use in terms of entropy. Okay. Now let us understand how this probability of error affects our channel capacity. Now in the y-axis we are taking channel capacity C. In the x-axis we are taking the probability, right? So when the probability of error is 0, channel capacity is maximum, 1 bit per use. And if we see here, we keep on increase the probability, we are able to see that the channel capacity is keep on dropping, right? When we are taking 0.1, it is some around 0.8 here approximately. So if we take 0.2 here, it is again around some 0.6. So keep on decreasing, right? So this is case 1. Case 2, when my probability of error becomes 0.5, the meaning is that the probability of correct reception or the erroneous reception is nothing but the 0.5. It may be correct, it may be wrong. In that case, my entire channel capacity is broken, where the channel capacity becomes 0, right? And when I keep on increase the probability of error, it is interesting to note that again the channel capacity is increasing, but remember that we have to flip the value. It is the probability of wrong transmission. That is, 0 is transmitted as 1 completely, 1 is transmitted as 0 completely. It is not like 50% possibility. 100% 0 is transmitted as 1, 1 is transmitted as 0 means we can understand that in this case, whatever answer we are getting or whatever bit is received has to be flipped, right? So we can have the channel capacity as maximum here, though the probability of error has reached to maximum value 1. Just we have to flip the output, right? So there are 3 cases here, what I discussed here. So case 1 shows that when the channel is noise free, that is P is 0 means we have seen that the channel capacity attains its maximum value of 1 bit per use, right? Which is exactly the same information. Whatever information is you're transmitting 0, it is received as 0. You're transmitting 1, it is received as 1. Case 2, when the conditional probability of error P is equal to 1 by 2, right? So the channel is broken. We are not able to predict whether the output is 0 or 1. The channel capacity attains minimum value of 0, which we have seen in the graph. Case 3, when the conditional probability of error is greater than 1 by 2, it is keep on increasing. When it becomes 1, Due to the channel noise, the channel capacity increases and reaches to 1 bit per use. The meaning is we have to flip the output. 0 is transmitted as 1, 1 is transmitted as 0, 100%. Right? So that is case 3. That is the meaning of that graph. So as a summary, in this video, we have learned what is channel model, why it is important, different types of channel model, a special case and a simple binary symmetric channel we have seen. We have analyzed the channel capacity of binary symmetric channel. Thank you.